So yeah, I'm going to be talking today about reinforcement learning for Gran Turismo. Sony's given a bunch of talks on Gran Turismo already, so I'm going to have a slightly different spin on this. So that's the success and sharp edges. So what I want to kind of focus on is what were the things that were kind of critical to make this project a success, and also why is this actually still hard, and what do we need to do in the future to make this work better? So I kind of like to start this just like with our humble beginnings. When I started my grad program, mountain car was the thing. I was doing mountain car all the time. I hope most of you know this. I hope it's not so antiquated now that you some people don't know. But you just want to get the car to go to the top, and it has to go backwards to get some momentum before it can go forward. And I feel like I've solved this problem so many times, or had agents solve it, that I really want, when I die, on my tombstone, just a counter that just has like how many times I've actually solved this domain. But that's where we started. And then this is where we ended up fairly recently. We went from this really simple car-ish environment to Gran Turismo Sophie. Gran Turismo is a really hyper-realistic racing simulator. It's not just a game. Like, they really spent a lot of time trying to make it accurate. And we outraced the best Gran Turismo racers in it. So this... Oh, the zoom thing, huh? Where's my cursor? Yeah, let me just move it to the other screen. I think it's this way. There we go. Cool. Yeah, so huge progress. This is an actual game. It's running in the game. That was a competition that we did against the best players, but we didn't just stop there. This wasn't just a research project. We actually got this into the game. So this is a trailer for the latest version of it. We keep updating and adding more features. And so this is not just a research project. We have people, you can go play it now on a PlayStation 5. You can race against an agent. It's a different agent. The first agent in the competition was designed for maximum speed, beating the best players. This one, not quite as much, because most players are not the best players, and so you don't want to just trump them very easily. So it's a different agent, bunch of different features, a bunch of things we've done. A bunch of other people in this room have worked a lot on making this happen, and there's still more coming out with it. So this is all really fantastic. In some sense, we feel like, well, we've done it then, right? We've gone from just reinforcement learning being this kind of academic curiosity, and now we have it in actual games working. That's it. From now on, we're just going to have reinforcement learning games forever, right? Well, maybe. I feel like there is a problem here, though, through this whole process. And this is the front page of our Nature paper. There's a hint on this. And if I zoom in, and I zoom in, you can look at this authors. It's not us. We're not really the problem per se. It's that this was way too hard. It took too many experts to do this, and it took too long to do it. It's like a 2-year project just to get to that competition. And that's not going to fly for actual game development. We need this to be much more straightforward. So that's kind of my main theme I want to express in this talk, is for reinforcement learning to really revolutionize gaming, it has to be a lot more robust and straightforward to use, or game developers are just not going to pick it up, right? They can't rely on this team of reinforcement learning experts who've been doing this for a long time to actually make it work for their game and spend a lot of time doing it. That's just not going to go. So things that matter to get there, and why I'm still grumpy, because I want them to not matter so much. There's a whole bunch of list of things here. I'm going to touch on all of these in this talk. There's surely more things I just didn't put into this talk, so if you talk to me more, I'll probably just be grumpy about other things as well. So feel free to get me going on that. But let's start talking about some of these. One of them is, of course, compute infrastructure matters a lot, and it's a weird compute infrastructure compared to what most ML does. Most machine learning, LLMs, what have you, they're like, well, we got our A100s, we're done. We just train. We have to vectorize it. There's a lot of hard engineering there, but we have different engineering problems, because we had to run this game, like the actual game, with rendered nodes, and getting rendered nodes that can render your game is non-trivial. And that's even though we actually used state variables from the game engine. We still had to run the real game, because headless versions of games don't really exist in the way you want them to, and if they do, they don't work the way you want them to. So we had a whole bunch of these clusters of PlayStation 4s talking to Linux machines that were then talking to a trainer that had like an A100 on it to do training. And so there's a lot going on there to build that whole compute infrastructure to do this training. So some gotchas to kind of take away from that. We did not, we had to run in real time. We could not run at 1,000 frames per second, kind of what Julian was talking about earlier. This is very slow. And so we didn't have there is no headless mode. We had to run the actual game. Game developers aren't really interested in making the headless version. And so that has a lot of implications. The big one I want to highlight is sample efficiency still matters. A trend in reinforcement learning lately is we have these really, really, really fast vectorized environments where we can just train the agents really fast. Those are great for doing experimentation and testing out algorithms. But I do worry that people will get a little distracted by that and think, well, that's the problem, right? All I need to do is I can run this just really fast and we're done. You're not going to run these games that fast. If you actually want to put this in real games, which is a simulation itself, right? It's not like even reality, which runs its own time rate. You're just going to have to deal with things being slow. And so that, care about sample efficiency still. Don't think it's solved because we got these fast vectorized environments. As far as the algorithm we used itself, we used a version of soft factor critic. So that is an off-policy algorithm that lets us be a little more sample efficient than maybe some other on-policy algorithms. We had some tweaks to this. So in particular, we used quantile regression. So we call it QRSAC. So instead of learning the expected value of the future discount reward, we were learning a distribution using quantile regression. And we also used n-step returns, where we don't just look at one next step, do the reward plus gamma times the next value of the next state. We would jump ahead a bunch of steps, sum up the discount reward, and bootstrap from the end there. And that's actually doing it kind of wrong. We didn't correct for any off-policy distribution mismatch for doing that. We just did that. And it helps a lot. So this is a plot looking at whether we use just regular SAC or this quantile regression SAC. These are lap times of the agent. So we have SAC taking 115 seconds versus QRSAC taking 114.47. That doesn't sound like a big difference, but in racing, that's an eternity. So this is actually the difference between a very, very good racing agent versus not. N-step returns also mattered a lot. We used 5 for the actual competition, but maybe arguably you could have gone higher and it still would have worked a little better. So that all sounds great, right? But why? Why did this matter? I don't really know. QRSAC usually we often find works better than just regular SAC in a lot of environments, but not all the time. We've looked into why the situations might work, build a bunch of hypotheses. Other people in the community have tried to investigate the theoretical reasons why distributional RL might work better. I don't think anyone really has a satisfying conclusion that works out. And since it isn't just always strictly better, that also puts us in an awkward position. N-step returns, all I can figure is deadly triad, off policy, hard. That's the best I got. But it's a little sad because we're actually not doing things theoretically correct here, and it still works better than doing the one-step returns. What do we need to do from there? I think we need more consistent off-policy algorithms that just kind of work with less hyperparameter tuning and an understanding of when they're useful. Even if they're not useful all the time, knowing when they're useful would go a long way. And I say off-policy, but that doesn't necessarily have to mean model-free off-policy. Model-based reinforcement learning is a very good alternative, I think, where you can get the same effects of I can train on arbitrary data, but I do all my planning in my learned world model that's on policy. So you get the data you get is off policy, but the learning is on policy, and you get to have your cake and eat it too. So that's another possible direction to go. Another big item was reward engineering was really, really hard. I hate this. This drives me nuts. These are all the terms we had in the competition with their weightings. You'll notice on some track car combinations, we actually had slight differences between them because that also mattered. That's all deeply unsatisfying. And there's a bunch of things we could talk about probably endlessly about this. I'll point out a few things in particular, though. One thing that's really hard here is this kind of group are all kind of related to sportsmanship and how you maneuver around other cars. This one's hard to define because not only are we trying to engineer things that make the agent learn well, we're trying to figure out what even the definition is. The sportsmanship of when it's okay to hit or not hit someone is very, very complicated racing. In actual competitions, what happens is they have referees watching. They kind of watch to see what actually happens after the collision and decide, I think that person was at fault, or they messed that person up. and trying to figure out what that function is really, really tricky. So this is going to be in games, I think, a constant problem where we have these complex environments, and whether something is adhering correctly is just going to be difficult to define to begin with. But even setting those things aside, just this engineering was very irritating. So if you took one of our reward terms, which was a course progress reward term, where what we do is we say, let's project where the agent is in the center line of the track right now, then we see on the next state where they are, and we'll just take the difference of the distance along that center line. And that's the reward we give it to go fast. Now that's not necessarily a great reward function, because really what you care about is like just finish the whole race as fast as possible. And in fact, when you get to the final stretch of the race and you're racing other people, you don't need to set yourself up well for the future. You just need to do well until you cross that line. So you might want to do something slightly differently. So you might want a reward that's just like cost function, and then you finish, do it as fast as possible. And this is not that. So you might say, OK, so maybe we can get close to that. If you need this for learning, maybe we could do good old potential-shaped reward functions, which is this classic way of like, oh, it won't distort anything. This looks like a potential shaping already. It's just missing a discount term. Can we do that? No. We tried that, and it failed miserably. The agent never even learned to get around the track. Potential shaping does not really work well. I could talk about that. You can come talk to me more if you want to hear more about why I think that is. But the gist is potential shaping kind of wants to eventually evaporate its shape as you do training. And so if you're training a lot and doing a lot of update steps, you kind of lose the benefit of it very quickly. So that's not a good solution to our reward engineering problem either. So I think what we need is alternative methods to do shaping rewards, or maybe if we're going to stick with shaping rewards of some sense, we need better ways to specify what those are than just kind of hacking around and seeing what works. Feature engineering. So as I said, we used state variables coming out of the game engine. There's a bunch of variables we get about the car, as you can see here. I won't go into all of them. There's also state variable representations that are really important for how we represented opponents. So what we basically did is we ended up with a representation where we took a list of cars ahead of you and cars behind you, sorted them by kind of rank, and then you have like a bunch of features about them, like their relative position to you, and relative acceleration, and all that good stuff. Choosing the features was also just extremely important to get good performance out of the agent. And just to kind of give you a taste of what that's like, we actually did 2 competitions. We did the first one, we did OK, but we didn't win. And then we did a second one where we won against the best racers. And the first one of the problems we had is our agent was quite fast, but often just kind of like hung around when there was a car in front of it. And what we found was we had in that kind of list of cars, one of the features at the time was an is occupied feature to tell whether that cell is actually filled with meaningful car data. And what we found through a bunch of analysis is we were like overgeneralizing that feature, and it kind of just got very conservative because they didn't want to hit cars or whatnot whenever cars were near, and we just didn't have enough information about that. So removing that feature actually helped a lot, and that feels wrong, right? Like removing it's just telling you whether there's a car there, but removing it actually made this agent more competitive. So that's just one of the weird, annoying things about feature engineering. So this matters a lot. We tried lots of other things I haven't talked about here, but this is where we wound up, and choosing this set mattered a lot. Other games are not easier than GT that we've tried to do this stuff on. There's still lots of feature engineering that goes on. So this is kind of not the deep learning dream where we just throw in features. Who cares? As long as they're just kind of correct, the deep model will just learn it, and life is great. So that's not happening. So what can we do about this? Maybe vision-like features. If we can find a representation that kind of works for all games, not just your particular game, that would be great. And maybe vision-like features can do that. But we don't want to be really slow. We don't want to have to worry about solving all the complexities of pixels and all that. And we do want to benefit from state data when it's available. So finding a hybrid kind of representation for that seems really important. And I'll note we have done some work on that. So we had a follow-up paper where we did train the agent using vision. These are just 64 by 64 pixel images. This is just pixels, and we had a small state feature vector as well. And it could learn very impressively to still race around other cars. So this seems like it might be a good direction, but there still might be more to do in terms of how we think about getting state data in here. So one other thing I wanted to point out is games these days have a lot of accessibility options. So this is God of War, where it's basically just highlighting in colors the semantic pieces of the environment for the player. We can probably have game developers build these things and give us nice semantic representations in a common vision-like representation and kind of build from that same representation across games. So that might be another way to do this. So yeah, that would, if we do that, it can kind of inform the neural network. I will add a few notes here about the neural networks we used. In the competition, it was just an MLP. It was like 4 layers of 2048 by 2048, or 4 hidden layers. We tried a bunch of other architectures. They didn't always work well. In fact, sometimes you might see a new fancy architecture that's getting great results in benchmarks. We go in, try it out, and it didn't work better than our just dumb MLP. That's kind of frustrating about why that is. And some of it might be that it's because, well, we've tuned everything around this network architecture already, and so maybe that's why it just works well. I don't know, but it's just an interesting thing to note that you can't always just take a new architecture from literature, put it in your environment, and it will work better. Like, that often does not work out. We do have variations in this architecture now for what's running in production. I won't get into that, but it's still fairly simple, nothing terribly exotic. Yeah, okay, running the gauntlet. This is another thing that you don't really think about when you're doing just RL in academia, which is like, well, we have our learning curve that goes into the plot, and that's what we show. Hopefully it was higher than everything else. For the game, you have to pick a policy, right? So you have this whole learning curve, and you eventually have to deploy a policy that's going to run in the game. And oh man, is that hard. And it's hard because there's so many different things that happen, situations that matter in the game, but they're kind of sparse and rare. And what you need, though, is you need a policy that kind of does well on all of them. And our current RL methods aren't super great at that. Like, oftentimes it forgets certain skills and then learns them back. And so finding that was really hard. So we set up this whole gauntlet where we take a bunch of different seeds of runs, scan through all their different policies that they had. We'd filter out the ones based on metrics that looked pretty good. Then we'd run them against each other in this anathlon with a bunch of different metrics that we track, and then we look for like a Pareto frontier of that, and then we pull those out, and we race them against each other more directly, choose the best ones, and do human tests against those policies. It's a lot. It's very exhausting, and we stared at a lot of spreadsheets when we were choosing these policies. So this is not always a lot of fun. I think you're going to have to do something like this no matter what if you're going to deploy something into an actual game. But if our algorithms were a little bit more monotonic in their behavior, this wouldn't be quite so hard to do. I always think back to just classic policy iteration where you just get every state you get this nice improvement over the previous iteration. We don't have that happening in our RL algorithms now. Maybe there's things we can do about how we organize our algorithms to be a bit smoother as they improve. Similar kind of set of thing. Well, to address this kind of problem, we used multiple experience replay tables. So they all shared memory, so we didn't duplicate memory, but we'd have a whole bunch of different replay tables for different kinds of situations the agent would find it in. And then we'd run our data, we'd shove it into the right table. And when we do sampling, we do stratified sampling where we sample consistently, like everything gets represented in our single batch of data that we would shove through the training. And this actually does at least smooth out the consistency a lot. It doesn't give you the new best, greatest performance, but your learning curves and that anathlon set of results will tend to be a bit more consistent when you do it this way. And I'll say we use this kind of technique a lot in a lot of our projects now, so it's kind of sticky. So it's a nice way to make improvements, but I will note it does require some engineering effort, which is not always super satisfying. You have to figure out what those scenarios are and go from there. We have a bunch of work. I think we've published some of it on ways to extend this and make it a little easier to do, but it does require some engineering effort. And another thing that's really nasty is the opponent distribution. If you're playing against other agents, or you're racing against people or other versions of our policy, the opponents you play against matter a lot. We didn't just do a very straightforward kind of self-play. We had a very curated self-play that we used. And what this plot is showing is on this x-axis is the kind of team score, which is basically just we have groups of cars under one policy versus other groups of cars in another policy. We'd race them against each other, and we give that kind of policy a score about how well it did in the race. And on the y-axis is also this questionable collisions metric, which is like, maybe you're not being very sporting in your racing, so you won, but you're going to get like, red flagged or black flagged or something. And so what we found, for example, is if you trained an agent against other agents that were very aggressive, that's these green ones, it didn't get into a lot of collisions. But it also really wasn't very competitive. It just became very paranoid about other cars running into it and just kind of like would back away. So racing against too aggressive opponents could be pretty dangerous. If you race against their built-in AI that they have in the game, that's very friendly. You get pretty good performance, but you don't learn how to race against other opponents who are also competitive themselves. And so we had a baseline where we had like curated policies we had trained in the past that we'd use as opponents, and that would work out as the best combination. So this is just a brief example. Again, during our first race, we didn't have enough data about the different kinds of opponents we had to face in the race, and we had this very annoying situation where we had overtaken one of the opponents in the race, and then we quickly lost the place right afterwards, which is not what you would expect. And we found out because our agent just hit the brakes. Like it passed it, and then he got aggressive, and it hit the brakes and kind of moved out of the way. And that was very painful to watch in real time. So, training lots more, really curating your distribution of opponents you're racing against helped a lot. We went forward to squelch that kind of behavior. So I've now named a bunch of different things. Is there a kind of research path we can take to solve some of these? Maybe here's a sketch of something we could do. One, I think if we can find a consistent set of features or representations across different games that we could use and build a model architecture around it, that would be really nice. And then from there, we can work on what algorithms we want to use that are like good at sample efficiency, more consistent, where less hyperparametering, and kind of side by side with that, maybe find alternatives to reward engineering where we don't have to rely so much on just plugging in the right kind of reward numbers to get the agent to learn well. That might be a good path. And we can do all those things then. We might be in much better shape for applying RL to games in the future. So just to kind of come back to where I was, main thesis here is for RL to revolutionize gaming, it has to be much more robust and straightforward to use. But I do want to note that we can do this. Like it sounds like a lot, but I totally think we can do this. Like again, cycling back, this is where I came from when I started in reinforcement learning. This is so much progress. So even though there's a lot of challenges here, I absolutely believe we can work on these things and make it better. And the last point then is, and it's totally worth it. These are some like quotes from just players on the trailer and other places when like the latest version of GT Sophie came out in Gran Turismo. The gaming community is extremely fickle. I was not expecting a lot of positivity, but we got kind of overwhelming positivity. People really love this feature. And so it really shows that using reinforcement learning to make these more intelligent and lifelike agents in the game matters a lot to the game industry. So we should definitely work on it. All right, and that's it for my talk. If you want to find me, I run a reinforcement learning website called Decisions and Dragons. I'm also on Blue Sky. Got some Sony links there at the bottom. We do have internship positions that open up relatively regularly, so take a look if you're interested. All right, thanks.
Thanks a lot, James.
Sure thing.
Awesome presentation. So we'll take questions for 5 minutes, and then we'll have minutes. Yep, please go.
I actually have 2 questions, if I can.
Yeah, of course.
First question. First, great talk.
Thanks.
And it was a fun. I agree with all the problems that you shared. And for reinforcement training to revolutionize games, we need something more.
Mm-hmm.
But I didn't see anything in your talk about working with developers and designers. Because in my experience, these are... Sorry.
Forgot that. Use this, please.
Can you hear me?
It's just for the recording.
Ah, it's for the recording. Okay, sorry. Can the recording hear me? Yes. I forgot.
You're
what I was
talking about developers.
Talking about developers, yeah, because these are problems that I also have in our experience, but they are bigger problems if we think about designers and developers. For example, let's take the reward engineering thing. Reward engineering is hard for reinforcement learning expert. Imagine if you give these tools to designers and developers. It's going to be impossible. So first question is, what's your experience in working with designers and developers to solve or to?
Yeah, it was definitely a very involved process. We were meeting with people at PDI who make the game probably weekly or bi-weekly or something, especially as we were ramping up. For production, we're still lots of meetings, and there's still lots of painful discussions about tuning the agent to work right. So finding, that is the other thing, is it's not enough to just say, here's an agent, it plays the game well. It has to play the game in a way that's fun. And so there is a lot of extra work we did on trying to figure out what does that mean. The developers, like PDI was very involved with us, and so that was great. But I do think that is a special kind of case. Like, I don't think long-term that's sustainable, and we have to be able to give tools that are just more straightforward. And that's why I want to kind of maybe find an alternative to reward engineering in particular. So one possibility is if we can have play testers, like here's the examples of how to play, and learn just from a very small number of demonstrations, and not do behavior cloning. We're still doing RL, but we use those trajectories to kind of bootstrap the process so it can find actually what's good. That might be a better path, but that means we need to kind of build our algorithms around being able to do that. I don't think our algorithms are super well suited for it right now.
Thank you. And the second question is, so you said, if we go back to your presentation, you said that, for example, the headless builds of games do not work well, right?
Sorry, the what of games?
Headless.
Oh, yes,
builds.
the headless, yes.
And it would be really nice to have headless builds to train reinforcement learning agents, but they don't work. And I agree, they don't work most of the times. But don't you think that for gaming industry to use reinforcement learning, don't you think that gaming industry has to change?
No. I think it's the wrong way to see it. We're there to help them and add something more. Game developers are extremely topped out as it is. So if we go and be like, hey, you got to build this whole other mode for us, they're gonna be like, nah, I got deadlines. Like, we kind of need to show them, like, here's an actual tool that makes your life better right now.
And then okay. Let's discuss it later.
Okay.
Thank you.
Thank you. Can you please hand it over?
Sorry. Hi, thank you. It was a very interesting talk. Can you share with us a little bit more on the compute requirements to train the best policy in terms of GPUs, number of PS4, training hours?
So let's see. I do have that somewhere in here. Let me actually see if I have it in my notes. I do. I just need to scroll the right thing. So yeah, so we had like a mix of training components. We had like V100s and we had some A100s. We had A100s. We'd use like half an A100, and that would be used for training one set. And then we'd have, I think we were up to like 20-some, let's see if that's right, like 20-some rollout workers, but that gets a little funny. Yeah, that's right. We had 21 PlayStations basically, but for a single run. And on that though, because we're using state variables, we could actually control multiple cars on the track, and so we could like get up to at max 20, but you have to like do a bunch of splitting and moving around. So it could vary from anywhere from just controlling one car on the track to controlling up to 20 cars on the track. So yeah, that's about where we were. And if you took all the real-time experience, it'd be like 2 years cumulative real-time experience to get to that. You can get to good behavior better than me actually much sooner, but to get to that actual superhuman just took so much longer to get there.
So, thank you for a great talk. My question is on the reward engineering. That reminds me the board games, like Game of Go, where the simple maximization of win or lose will generate the superhuman agent. And I think the largest difference is the planning algorithm. So they use the MCTS. And my question gonna be, do you think that planning algorithms will compensate such, nasty real modeling stuffs? And is it possible in Gran Turismo? Running MCTS.
If Probably not MCTS explicitly, because Gran Turismo is continuous action, so I have whole opinions on that. That's a whole separate matter. I do think planning can help if you do model-based reinforcement learning, and then you can do some powerful optimization in your world model. But I don't think that's really what was why Go could work well. So Go is actually, it sounds sparse. It's not a sparse reward function in the way that matters to the RL algorithm. So in the way that works, you do a rollout to the end, someone wins, right? And if you're playing against yourself, about half the outcomes are going to be you win, half are going to be they win. That's a very rich reward signal that you can bootstrap from. In Gran Turismo, you cannot roll out to when you finish the race. It's just way too long. The horizon is just massive. And so I think what was nice about Go is it's a simple reward function, but it's a simple reward function that actually turns out to be pretty dense, and that works out well. And so we're still in that we need dense reward regime to do well, or you need to start with a policy that somehow sees the right things from the beginning. I think that's why reinforcement learning with LLMs is working very well. As you start from a base model that kind of has already got the support over the relevant things, and then you're just whittling it down.
Yeah, thank you.